Time? Good. Okay, so we left off last time there. So we left off last time here that we found that when a covalent bond was not the same, the bond becomes polar. And these electrons, where the dots represent electrons, around chlorine there's 8 electrons. Around hydrogen there's 2 electrons. Chlorine has satisfied its octet. Great. Hydrogen has satisfied what it considers an octet because it only has the 1s2. So it fills the 1s2, it's happy. Fills the 1s2, it's happy. Oxygen in this case, chlorine in this case, chlorine fills its 3p6, oxygen fills its 2p6. They've both got an octet when they bond. If that is clear, give me a thumbs up. I want to make sure that, because that's a good building block. If you have any questions about that, wave your hand around. Okay. Now we look at the bond and we can say, is this a polar bond or a non-polar bond or an ionic bond? If you have a metal reacting with a non-metal, it's going to be an ionic bond, where the electron is literally removed from the metal, taken to the non-metal, and you have a positive and negative that sticks together, like in our model here. Sodium gives away an electron to chlorine, sodium becomes positive, chlorine becomes negative, and they stick. You get a whole bunch of them stuck together, and we call that a crystal lattice. Okay, now once we know that a bond is polar, the real question we want to know is the molecule going to be polar? And the way we determine that is we add up the bond dipoles. This is a dipole. It's an arrow that points from where the electrons have been pulled to where they have been pulled. So this is where they have been pulled, this is where they're going. So this is a partial positive because this area is negative with all these electrons right here. Partially negative, partially positive. I don't know what those 2 electrons are doing there. We'll take those away. So partially negative, partially positive. The dipole points from the positive to the negative. And it's just an arrow. You make an arrow, and then you say, this is the positive end. And when you put the partial signs in, the partial sign is like an S little loop at the end. This is the partial positive. This is the partial negative. So far, so good? If you understand the bond dipole idea, give me a thumbs up. If any part of the bond dipole idea is unclear, now's a great time to ask a question. Okay? So, we take all the bond dipoles, we add them together. Now, just like in a tug of war, if one person is tugging that way, and one person is tugging that way, if one dog is tugging that way, and one dog is tugging that way with the exact same tug force, the rope doesn't go anywhere. And that's what happens in a non-polar molecule. The 2 dipoles will cancel out, and they won't go anywhere. If they don't cancel out, then we're going to have a polar molecule. So dipoles are considered vectors. This is the same kind of vector you learn about in math. It's just an arrow representing a force or a push or a pull or a movement of some kind. So if you have multiple bonds that don't cancel out, they will sum up to make a polar molecule. It only happens when you have an asymmetrical molecule. Do you know what symmetrical means? If you know what symmetrical means, nod your head. No. Okay, so symmetrical means you can cut it in half and it's going to look the same on the left and the right. With a molecule, symmetrical means any direction you cut it, it's going to look the same on the left and the right. Asymmetrical means it isn't. So a good example is, this ball is symmetrical. You can cut it any way, it's going to look the same. This cone is symmetrical only in 2 axes, only in the y and z axes. Or I guess in this case, yeah, the z and the y axes. But symmetrical means you can cut it, it's going to look the same. Now if you look at water, let's thin this out a little bit so you can see everything that's going on here. There we are. Let's get rid of this. I'll redo that. All right, so here's our water molecule. And our water molecule has two bond dipoles. There we go. This is oxygen. I'll put oxygen back in. Okay, so this has two bond dipoles. It has one bond dipole between oxygen and hydrogen, and another one between oxygen and hydrogen. So one bond dipole that way, and one bond dipole that way. Now this is where it's important. Which atom between oxygen and hydrogen is more electronegative? And remember, electronegativity goes low, high, low, high. So highest electronegativity is fluorine in that direction, lowest is francine. So between hydrogen and oxygen, which one's more electronegative?
Oxygen.
Oxygen. You can also look and like, hey, oxygen has all these electrons right here. Oxygen is more electronegative. So we draw the bond dipole. So the electrons are going to be pulled towards the oxygen. This is going to be our partial negative, and the hydrogen then is going to be the partial positive end. So we have two bond dipoles, one pointing this way and one pointing this way. If you were to sum up those bond dipoles, what would the resulting dipole look like? Can you show me with your hand what it would look like? If you have one dipole going this way and one dipole going this way, what's the result going to look like if we add those two together? Imagine one linebacker pushes this way, one linebacker pushes that way. Where does the quarterback go? This way. All right. So the bond dipole is going to look like, or sorry, the molecular dipole is going to look like that. So these two are bond dipoles. And the result is the molecular dipole. So we would draw this like this. This is going to be the partial positive end. This is going to be the partial negative end. And that's what makes water polar. Those two bond dipoles add up together. They don't cancel out. So since they add up to something, that makes water a polar molecule. If you're with me so far, give me a thumbs up. Any part of this is unclear, raise your hand around. All right. Now, if they do sum up, then we have a non-polar molecule. And this happens when bonds actually cancel out. A great example of this is carbon dioxide. Because if you drew carbon dioxide, let's see, you would have an oxygen on this side, an oxygen on this side, chlorine in the middle, and I'll show you where all this comes from in just a little bit. There's dots, there's dots, there's dots, there's dots. So if you were to draw the bond dipoles between carbon and oxygen, oxygen is more electronegative, so it gets one bond dipole going that way. Carbon to oxygen, oxygen's more electronegative, it gets another bond dipole going that way. Those two bond dipoles are perfectly in opposition to each other, so they cancel out, and this is a non-polar molecule. Now, why is this important? If you want to dissolve something, you have to match it with similar molecules. The phrase we use is like dissolves like. If you want to dissolve something that is polar, you need a polar substance. If you want to dissolve something that is non-polar, you need a non-polar substance. So polar things dissolve polar things. Non-polar things dissolve non-polar things. Polar things also tend to dissolve ions because ions are charged. If you remember, the water molecules come together and they take away the ions. The positive sides of the water molecules surround the negative ion. The negative side of the water molecule surrounds the positive ion, and that's how things dissolve. We'll go into more detail about that later on. Okay, so that's what like dissolves like. Polar things dissolve polar things. Non-polar things dissolve non-polar things. What you will need to do a lot is determine if a molecule is polar. And the mental gymnastics you need to do is draw the bond dipoles. If they cancel out and the molecule is symmetrical, it's a non-polar molecule. If they don't cancel out and they sum up to something, you will draw the molecular dipole. In every molecule you make, you're either going to write non-polar or you're going to draw the molecular dipole. Is this clear? If you have any questions about that, wave your hand around right now. Because you're going to be doing this probably 50 times.
What do you mean when the dipoles sum up?
So if this bond dipole adds to this bond dipole and they disappear because they're opposing each other, they're either pointing this way or pointing this way, then that's a non-polar molecule. But if they don't, then they sum up. Like, imagine one person pushes this way, one person pushes this way, the resulting push is going to be this. So if the vectors, the bond dipoles, which are just like math vectors, if they add up and they don't cancel to zero, then it's going to create a molecular dipole, which is the result of the bond dipoles. Does that answer your question?
Mm-hmm.
Okay, off we go. Any other questions before we move forward? Boop, boop. Okay, trying Lewis structures. So Lewis structures are pretty cool. It's when you ever see like, hey, that looks like a molecule, it's with the sticks and the lines and everything. That's a Lewis structure. Chemists eventually they simplify the Lewis structure, but if you're looking at something and you have a bunch of arrows and dots, that's a Lewis structure. So that carbon dioxide is Lewis structure. So this is what you do. You determine how many valence electrons are around an atom. Super important to remember valence electrons. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Group 13 has how many? 3. Group 14? 4. Group 15? Group 18? So 1, 2, 3, 4, 5, 6, 7, 8. You determine how many valence electrons you have. And then you answer the door. Hello. Yeah. You determine how many valence electrons you have, and then you put them around the atom, starting at the 12 o'clock position and going clockwise twice. So if your atom is here, you start 1, 2, 3, 4, 5, 6, 7, open. 1, 2, 3, 4, 5, 6, 7, 8. And then once you have the dots around an atom, you just move atoms around, and we're going to do this a lot on computer and in real life, or in computer and models, with these really cool plastic models. And you move them around until everything's happy. Every atom has satisfied its octet, or hydrogen, which has got 2. So, this is what you do. Determine the number of valence electrons. I think we're going to use chlorine as an example. Valence electrons turn into dots. The dots represent electrons. And then you share the dots until each atom has an octet, or hydrogen has 2. Boron is special because it only has 3 bonding electrons. So boron will always look like that. It doesn't have any unshared pairs, doesn't have any anyway. So, and then pairs of electrons between atoms are called bonding pairs. With electrons, everything is pairs. Because it's all just they share. Because one shares this one shares that. So the dots between atoms are called bonding pairs, and those get turned into sticks. There's chlorine with 7, there's chlorine with 7. They come together and share. That bonding pair becomes a stick. Electrons that are kept to a single atom, it's like, I have 2, I'm going to keep them, are called unshared pairs or non-bonding pairs. Sometimes you even hear them called lone pairs. Oxygen here listen carefully. Oxygen has 2 bonding pairs in the water molecule. Oxygen has 2 bonding pairs in the water molecule. Oxygen has 2 unshared pairs in the water molecule. Bonding pair, unshared pair, unshared pair. If you can see that 2 shared, 2 unshared, give me a thumbs up. Because this is really important. If you don't understand this, you're going to struggle with this entire unit. Questions? Okay. Because Google messes up the animation. I'll start again. There's fluorine. Chlorine's got 7 electrons. 1, 2, 3, 4, 5, 6, 7. Those electrons are turned into dots. 1, 2, 3, 4, 5, 6, 7. And that's what it would look like. You don't need to make the dots that big. Oh, this is one of the first PowerPoint animations I made almost over 20 years ago. It's completely broken because when I converted it to Google Slides, it just completely broke it. But there you go. 1, 2, 3, 4 around carbon, 1 each around hydrogen. Again, carbon is 1, 2, 3, 4. You start at the 12 o'clock, you go 12, 3, 6, 9, 12, 3, 6, 9. Then you combine them, and when you combine them together, they end up looking, they get the sticks, or the dots turn into sticks. 1, 2, 3, 4. This is methane, CH4. This is ethanol. Methane does not have unshared pairs. All it has is bonding pairs. Ethanol, that's grandma's medicine. That's the drinking alcohol that kills you slower than the other alcohols. Ethanol has 2 unshared pairs around oxygen. And it has 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8 bonding pairs. How many bonding pairs does methane have? 4. If we were to draw these, now this is super important. If we were to draw these, please don't talk while I'm talking. If we were to draw these, we would realize carbon is more electronegative than hydrogen. So we have a bond dipole there. We have a bond dipole there. We have a bond dipole and a bond dipole there and there. So that's a bond dipole, that's a bond dipole, that's a bond dipole, that's a bond dipole. Again, bond dipoles go from the partial negative to the partial positive, and we show the positive with a line like that. Do these bond dipoles cancel out? Yeah. This cancels this one, and this cancels this one. This molecule is non-polar because all the bond dipoles cancel out. If you can see that, give me a thumbs up. What about ethanol? So first of all, we learned about how these bonds are polar and these bonds are polar. Carbon to oxygen, oxygen is more electronegative. Hydrogen to oxygen is more electronegative. What about the bond between carbon and carbon? Is that a polar bond or a non-polar bond? Is it polar or non-polar? If you have 2 atoms sharing electrons, they both have the same pole. That's a PUL. They both have the same PUL. They both have the same electronegativity. So if you have 2 atoms that are sharing a bond, it's a non-polar bond. Neither atom can pull more than the other one. Okay? How are we doing? We're good? Okay, now let's cancel out some bonds and see if there's anything. See if there's anything left. Let's put our bonds back in. That one there, that one there, that one there, that one there. That's wrong. That one there, that one there, that one there, this one here. Okay. Now we're going to cancel out those bonds. Do you like yellow? Top and bottom, cancel them out. Top and bottom, cancel them out. Looks to me we have 3 bond dipoles that do not cancel out. We have one here that doesn't cancel, one here that doesn't cancel, and one here that doesn't cancel. So you take that to the right, and up, and what you do is you get a bond dipole that looks like that, or a molecular dipole that looks like that. Partial positive, partial negative. That is the molecular dipole for ethanol alcohol. All right, how are we doing? Bye-bye. Maybe. How about this one? Bye-bye. All right. So again, this is methanol. This is the alcohol that kills you real quick. So don't drink it. And again, start by adding dots around the molecule. Or sorry, dots around the atoms. And then arrange the atoms until everything has 2 around it, except for hydrogen. It only has 2 on one side. Turn those bonds to sticks. Then create the bond dipoles. Cancel any bond dipoles that cancel, and sum up any of them that don't. This animation should still work in when you download the video or download the slides from Google. This is when we had an animation class and we did computer animation. This is one of the first computer animations we did. Like, let's do flipper flip. Pretty cool. I did it in 2020 or 2021. Yeah. All right. If you have multiple bonds, or where do the multiple bonds come from? Again, remember this. Multiple bonds are shorter and stronger. A double bond is a shorter bond. It's a stronger bond. If you have multiple bonds, that means you have more valence electrons than places to put them. Carbon dioxide requires double bonds. I'll walk you through it. This is going to be the end result. So carbon dioxide, the first thing we want to do is write down the atoms we have. We got a carbon, and we got an oxygen, and another oxygen. How many valence electrons does carbon have? 4. 1, 2, 3, 4. How many does oxygen have? Same as being group 16, it has 6. 1, 2, 3, 4, 5, 6. Same over here. 1, 2, 3, 4, 5, 6. And some of you can realize right away that this dot can match with that dot, this dot can match with that dot, this dot can match with that dot, and this dot can match with that dot. And the end result is carbon, which has a dot, a dot, a dot, actually draw them this way, dot, 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 oxygen, dot, 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 oxygen, dot, 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 dot. I'll tell you why we draw them at an angle like that later on this week. And that becomes that. This is a double bond on each side. Carbon, oxygen, double bond. The bond has polarity just like any other bond. It just means a double bond is made out of 4 electrons, 2 pairs, instead of just 2 electrons, 1 pair. Acetylene is a triple bond. There are 3 electrons between carbon and hydrogen. Sorry, between carbon and carbon, and 2 electrons between carbon and hydrogen. All right. Questions? If you have no questions, give me a thumbs up. We'll move forward. Okie dokie. All right. Practice. Yay, practice. Here's the instructions. Determine each atom's weight of electrons. Arrange till all atoms except hydrogen have 8 valence electrons. Hydrogen has 2. And what you should be using, replace dots with sticks. Carbon's in the middle. Add bond dipoles. Total the bond dipoles to create a molecular dipole. If you have a molecular dipole, draw the dipole. If you don't, write nonpolar. All right. work with on these in your notes. If you need scratch paper, there's some over. There was some over there. I'll get some more. There we go. Here's my scratch paper. Does anyone need scratch paper to scribble these? Hand these back to Ryan. Anyone else? All right. Scratch paper over here. Okay, so take some time, scribble these out. Again, write out the atoms, give the atoms their dots, and then turn it into a puzzle. You're on your way, yes. So then put them together. So you're going to have your hydrogen and your bromine are going to be connected like this. So
okay. So
that,
they're just.
yeah, just finish it up. And when you finish it, maybe remember how many dots an atom has to begin with. Make sure they stay together. So these two dots become sticks or bonding groups. But this pair, and this pair are Yes. Okay. In the before time, I would have you guys come up and put your work on the board. But I know that's not going to work. Not in this class anyway. So we'll start with hydrogen and bromine. Hydrogen's got 1 dot. Bromine's got, how many valence electrons does bromine have chilling out between chlorine and iodine?
3 or 6, 7.
7, yeah. So fluorine, chlorine, bromine, iodine, those are our halogens. They have 7. 1, 2, 3, 4, 5, 6, 7. Pretty clear that that is going to go right there. So the next step would be to combine the dots. If you don't like to erase, and I don't like to erase, looks like that. And then that becomes hydrogen bromide. This is our bonding pair. And our unshared pairs are there, there, and there. Typical test question is this. This molecule, it's going to give you a molecule, you're going to draw it, has blank many unshared pairs, blank many shared pairs. So if I ask you, hydrogen bromide, HBr, has how many bonding pairs? 1. How many unshared pairs? 3. Context clues. An atom will never have more than, you know what, I'm going to let you figure that out. pH 3. So phosphorus is really cool because phosphorus has 5 electrons. 1, 2, 3, 4, 5. Hydrogen has 3 each. 1, 2, 3. This dot goes there. This dot goes there. This dot goes there. P, H, H, H. Unshared pairs. pH 3 has 3 bonding pairs and 1 unshared pair. C2H4 is interesting because you look at it right away and you're like, okay, that's not enough. That's not enough stuff. C, C, H, 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 H. 1, 2, 3, 4. 1, 2, 3, 4. Put the carbons together. Add some hydrogens. Oh no, I'm out of stuff. But these carbons have extra dots there. Those extra dots become double bond. Questions? And the rest is just practice. Yeah, that's it. What the? Oh yeah, that's it. Okay, so to check your practice, what I'd like to do for the other ones, just look these up online to check your work. So draw them, check your work online, and see how well you did. And that is everything we have for today. Questions? Okay, you can use the remaining 15 minutes to start work on worksheet 2, which is doing dots. Dots, dots, dots. Everybody loves dots. Industry, industry, bye-bye stream.